thanks for joining me. I'm Nadia, and I'm very happy to be presenting joint work with my advisor, Magdalena Ortiz, and my co-advisor, Mantas Simkus. Let's jump right in. So the overarching goal when dealing with description logics is to properly model the world, broadly speaking. And what this involves is dealing with numbers and strings, because nearly everything in the world has numbers associated with it. For example, measurements of time, volume, weight, and so on. And the description logic community has long recognized the need to properly model such so-called concrete features. And this led to massive research efforts being put into description logics with concrete domains. Now, for our purposes, a concrete domain is basically some numeric set, like the reals or the integers, along with some predicates that you can put on top of it. So a typical example would be to say that one feature is smaller than another, or that some feature is equal to some constant. And the problem with this is that it's very easy for reasoning to become undecidable, especially in the presence of T-boxes. Now, one of the ways to remedy this is to limit what you can say, what type of predicate you can use in the concrete domain. And there has been also a lot of work put into identifying which concrete domains maintain decidability in the presence of general T-boxes with some very general meta conditions identified, such as being omega admissible. But there has been kind of a glaring gap in this landscape, which was only addressed in 2016. And this is the lack of support of concrete domains that are based on the integers. And this is despite the integers being a very natural concrete domain to have. For example, when you're modeling dates or amounts of people, it doesn't make sense to have non-integer values. So, like I said, this was addressed in 2016 by Karapele and Turhan, who I believe is also presenting in the session. And they introduced ALCFP, which has all sorts of cool features in my opinion, but the big deal about it is that it allows you to incorporate integers with comparisons and equality to constants, and you get to keep general T-boxes. So actually this result is a special case of a very powerful meta theorem. And the thing is, what's important is that the proof of this meta theorem involves very heavy machinery and multiple chained reductions to bespoke automata models. And what happens is that along the way, you lose the ability to infer elementary upper complexity bounds on the problem. So, we were wondering, since it took so long to get this result with the integers, even though it was so sought after and pointed out in the literature, what would it cost to actually reason in the presence of integers? Surely it can't be easy considering how frustrating they can be. So it turns out that integers don't cost anything extra. And what I mean by this is that, concept satisfiability with respect to general T-boxes is ExpTime complete for normal ALC, no concrete domains, no nothing. And what we show in our paper is an ExpTime upper bound for this problem in ALCFP-Z, which is really the best that you can hope for. And how we do it is we use automata, but with a twist. So how did we do it? To solve this problem, you're actually solving two separate problems. You can manipulate your original concept, which has both the ALCF part and the integer constraints part, and turn it into two things: a usual ALCF concept, which you can check for satisfiability in whatever method you want, and a constraint graph, which represents the relationships between the features that you're talking about. And for that, you are solving an embeddability problem. So to be a bit more precise, the vertices of the constraint graph represent the features of your logical elements, and the edges in the constraint graph represent which features are smaller then the other one, and you also have integer labels that indicate that certain features are equal to some constant. And what you want to do is check whether you can embed this constraint graph into the integers. What it means is that you want to check whether you can assign integer values to the vertices in a way that respects the relationships encoded in the graph. So, for example, here you want to assign an integer that is smaller than the integer you're assigning here, and to this vertex you want to assign the constant 2. And typically, if you want to solve a problem like this using automata, which is what we wanted to do, you normally come up with some condition which captures the graphs you are interested in, so that the automaton you build will accept exactly the embeddable graphs. But we did not manage to do that. We managed to come up with conditions which were necessary, for example, that the graph is acyclic, which was easy enough, but we never managed to come up with a condition that is sufficient. We would always find examples of graphs which satisfy the condition but are not embeddable. However, these examples would always be irregular. They were never quite natural, and they would always hide some denseness that prevented the graph from being embeddable somewhere in the graph. And at some point, we came across this paper by Demri and D'Souza, which was brought to our attention by Carsten Lutz. And they were working on something similar with LTL. So they were operating over words while we are operating over trees. But what they said is essentially, forget about finding a characterizing condition. How about we use Rabin's theorem instead? And Rabin's theorem basically says this. If you have a tree language that is accepted by a Rabin tree automaton, then it contains a regular tree. And what this means for us is that if you can find a necessary condition for embeddability, which is sufficient for regular trees, then you're good to go, as long as the condition is verifiable with a Rabin tree automaton. Now, why does this work? Because if the automaton accepts some tree, then by Rabin's theorem, it accepts some regular tree. And because your condition is sufficient for regular trees, this means that there is some regular tree which is embeddable. And therefore your problem, is solved. So we thought this is a really neat trick. And we really wanted to apply it to our setting. So like I mentioned, this work was over words while we were over trees. And the main problem with that is that this denseness that kept our graphs from being embedded, when you're dealing with constraint graphs that are associated with words, they end up looking pathy. And then the denseness doesn't really have anywhere to hide. So it's relatively easy to detect, let's say, whereas in trees, it can hide all over the place, going up, down, up again, down again. And this is trickier to check using a Rabin tree automaton. So what we had to do is a bunch of work that involved combinatorics, and the details are in the paper, but we argued that when there is denseness somewhere in the tree, then there is also denseness in a pathy part of the tree, which allowed us to construct a Rabin tree automaton to check for denseness. And this is how we obtained our upper bound. We constructed a Rabin tree automaton that, we gave an explicit construction of the automaton that checks for embeddability. And this is where the ExpTime upper bound comes from. And what's nice about this approach of using automata, and this is generally true, and also for our case, is that it is fairly easy to adapt the work that you did to similar settings. So another thing that has been pointing out in the literature as something that would be very nice to have is that sometimes you want to be operating in general over the reals. Let's say you're modeling people, so you want to talk about their height and weight in real numbers, but you want certain features to be natural, like the number of kids they have. So it would be nice to have a predicate that says that certain features hold integer and natural values. And we were able to adapt our condition and automata to show that predicates like this can be added to the reals at no additional computational cost. And another nice thing about this logic is that you can talk about all the features associated to a logical element in one go. And it also gives you access to the concrete domain using any role you'd like. So the details don't matter so much. What I want to add is that these properties of the logic allowed us to add integer domains to existing formalisms and obtain new results on them by translating them into ALCFP. So even if you don't like this particular logic, it does imply new results on other formalisms as well. So to wrap it up, description logics with integer domains have been an open challenge for a long time, which was answered and then some by Carapel and Turhan, but without complexity bounds. And the talk today was about, now that we know that it can be done, how much does it cost? And we see that the answer is surprisingly nothing. I mean, nothing extra, plus some other results. Now, I am blatantly ignoring any encoding issues of the integers. So I'll just add that we do assume that our numbers are encoded in unary, but it's a little more nuanced than that, but I don't have time to get into it. Feel free to mention me on the Slack, and I'll be happy to answer any questions. Thanks for tuning in.